form of thermo before, you'll be, especially if you had chemical engineering, mechanical, civil, the sort of classic engineering disciplines, you'll be okay in the beginning. You'll recognize a lot of stuff. When we get more into material science, stuff like chemical potentials and phase diagrams, solution theory, some of that may be a little newer for you. The physicists among you, I'm sure you'll shine through the statistical mechanics part, because for many physicists, thermo is statistical mechanics, but the beginning may all seem a little odd for you. And I don't want to be patronizing, but you may want to just like very quickly read through a bit of undergraduate text, because it's just more about how material scientists think of systems and how they sort of make abstraction of reality to apply a thermodynamics problem. If you've never had thermo, this will be an intense ride for you. But the joke about thermo is that in the second class, you learn what you should have learned in the first class, and so on. And the reason is that it's a fairly abstract concept, thermo. You know, normally when you learn things, there is a stage where initial stage where you just learn the symbols and manipulation of the symbols and equations. And usually that keeps your brain occupied, and it's only when you free your brain of these things that you can start getting to the conceptual depth. And if you have to do all at the same time, that is not easy. It is not impossible, right? You're all smart people. But the way this normally goes, right, is that the people who've had thermo before, a lot of them will go like through this class, I finally get it, okay? And that's not because I'm such a great teacher, that's because you get it the second time. You know, they could put a clown in here and you would get it probably the second time. But if it's the first time, you got to do all these things together. Because one thing I want to tell you, I do not teach an undergraduate class. You know, this is supposed to be a top level graduate thermodynamics class, which means that you have to be able to apply thermodynamics in all its situations. You have to understand it. So this is not the kind of class where I give you an equation, you have a homework problem where you solve the equation, and then I give you an exam problem with other numbers to solve the equation. That is not this class, right? Thermo is a very difficult, it's mathematically a very simple subject. You know, we do first order differential equations, right? du is cv dt, right? I mean, mathematically it doesn't come easier, but it is conceptually hard. It is conceptually hard in the sense that it's abstract, understanding how you set boundary conditions for a system, figuring out which equations to apply to a problem is the hard part. The hard part is not solving the equations, okay? And that's maybe the one takeaway you should have from this lecture. When you look at problems, the biggest mistake you can make is look at the solutions to get the first line, because getting the first line is the hardest part. I feel like it could be a song or something, right? Getting the first cut is the deepest. No, getting the first line is the hardest part, right? So like, because after that it's just math, right? But the first line is a translation of the physical problem to the sort of abstract realm of thermodynamics. And we're going to come to that. I'm going to say it so many times they're going to be so bored of me. Okay. I think it's time for me to start. Oh, any questions on any of the sort of practical stuff? You know, if they come up later, you're welcome to bring them up. We're all kind of like learning as we go along here, how we run this class. So maybe Friday will be totally different. Who knows? Okay. Well, now I'm going to start lecturing, I guess. And since I'll have my back to the camera often, feel free to shout when you want to answer, when you want to ask a question. Okay. So, trick question number one. What is thermodynamics? So, in principle, all but one of you should be able to answer that, because there was only one person who said they never had thermo. So the rest of you had a whole class on something. So, you know, you should be able to answer this question, right? What is it? Like, let's say you go to a cocktail party. Wait, those don't exist anymore, right? So party, what is it? Dinner, cocktails. What is thermodynamics? Does anyone want to take a stab at it?
It studies heat and work.
Okay, I heard, I need a better speaker here. Something about heat and work. Is that what you said?
Yeah.
Okay, cool. Let's write some pieces down because I'm working. Anything else? Like, is there anybody who wants to attempt to give a formal definition of what it is? Oh, come on, do your best. Don't be shy. I won't bite your head off because I actually can't now, right? A good one. Flow of energy. So let me write my definition down and then we'll talk briefly about it, right? It's a macroscopic framework. It's amazing how dyslexic you become when you're on the board. It's a macroscopic framework of energy flows and there's sort of more, and how they affect or how they affect properties of the system. Oh, by the way, I forgot to tell you, on Piazza, notes will appear. They might have already appeared. They will appear before the lecture, so hopefully they're there. They're not like notes that I wrote, but the last 2 years, the GSI took notes in class. So 2 years ago, they took notes. Last year, the GSIs corrected those notes from the previous years. And then I went through them again to just make sure there are no mistakes in them. But they're sort of like a skeletal version of the class. You might find them handy because in the end, I don't change the lecture that much. You know, Thermo hasn't changed that much. So if you, you could use them, for example, as a base set of notes, and then you could mark them up with whatever I say. We'll make sure, if they're not there now, we'll make sure they are there before every lecture. Okay, so let's go back to this definition, right? There are a few important things in here. And this is kind of what you guys focused on, right? You talked about heat and work, which are forms of energy flows, and flow of energy. So clearly, that's stuck in everybody's mind, right? It's a framework to describe energy flows. And you will find that in thermodynamics, energy is the central coordinate. Energy is the coordinate. And everything we care about will be derivatives of energy. You know, forces and displacement and property. So, you know, forces, as you know, right, if you've done mechanics, force is a first derivative of energy with respect to displacement, right? Displacement is a derivative of energy with respect to force. Second derivatives will be properties, right? Things we care about like elastic moduli, compressibilities, heat capacities will be second derivatives. So energy will be the central coordinate. I use this word framework here. And you may wonder why I've picked that. And the reason is that in the end, thermodynamics is nothing but a set of equalities and inequalities. And this is important because that means thermodynamics is what we call NINO, nothing in, nothing out. Thermodynamics is a processor. If you put no information in, no information comes out. So this is unlike, say, physics. In physics, you have a fundamental equation that describes matter, say the Schrödinger equation, and you could literally calculate things about materials with that. It's a model for materials. Thermodynamics is not like that. Thermodynamics will be, I put in 3 properties and 7 other ones come out, right? Thermodynamics, because it is macroscopic, we'll talk quite a bit about that, it does not give you basic information about materials unless you put some in. And then it transforms it and you suddenly learn a lot more about your system. Okay. And then finally, I love colors. Let's see, what have I used? Green. It is macroscopic. So thermodynamics only deals with macroscopic coordinates, right? So if I have a piece of material, that could be the length, right? I could be the volume of that material. It could be the mass, right? You know, the how many kilograms of this. But there are other macroscopic coordinates that you could invent, like what about the radius of curvature? That's a macroscopic coordinate as well. In principle, these are all macroscopic variables. This is the greatest strength and weakness. You know, it's sort of like being smart, right? If you're really smart, you're only a step away from going over the edge and going crazy, right? This is kind of the macroscopic piece of thermodynamics. It's a weakness because it never will teach us anything about the microscopic nature of matter unless we put something in about it. But it's a strength that it does not rely on any microscopic definition of matter. And that's why thermodynamics is generally applicable. So the remarkable thing is that thermodynamics can be applied to the world, it can be applied to steam engines, but it can also be applied to a piece of material. And it's sort of a remarkable formalism, right? That it can be applied to all these things. And actually there's a quote in the notes, you know, Einstein was the guy who said that he thought of all the theories he'd ever worked on, thermodynamics was the only one that he thought would never be overthrown. He thought thermodynamics is the only theory that will stand forever. So, you know, welcome to the class that's going to teach you the ultimate theory, right? Okay. So, So what's the relation between thermodynamics and other things you've learned? So somewhere down here, you have macroscopic thermodynamics. By the way, I abbreviate thermodynamics as TD often, okay? And other things you've learned as undergraduates, you know, you've learned things like physics, chemistry, you know, biology, right? All microscopic definitions, all microscopic descriptions of the world. So this is sort of the triumvirate of microscopic fields, right? So the question is, how does thermodynamics relate to these microscopic fields? And the connector is made by what's called by statistical mechanics. So it is statistical mechanics that is the, both literally and figuratively, the integrator between microscopic descriptions of materials and classical thermodynamics. It is statistical mechanics that what it will do is, if you have a physical model for a system at the atomistic level, right? You have some atomistic behavior and interaction laws between things. Statistical mechanics will tell you now how to get macroscopic variables out of that. And to run ahead of the course, there is in principle 90% of the time that's one of two things. Either statistical mechanics averages over microscopic variables, or it integrates them away. Right? And if that doesn't mean anything to you, don't worry about it. We will show that in StatMech. But for those of you who've seen StatMech, you may sort of recognize that there's essentially sort of two fundamental principles to remove microscopic degrees of freedom. Okay. So I'm ready for the second poll. Jianyang, do you have it? So the next question is, who invented thermodynamics? So I'm giving you 7, do you see the poll coming in, Jianyang? Can you share your screen?
Okay.
Okay, let's not waste too much time on it. Okay, how about you read me the results then? So it's Jay-Z, okay. Okay. Okay, I have good news for you. You're all winners. Because, you know, thermodynamics was not really invented by one person. It was a slow and we always recognize Gibbs. We call it Gibbsian thermodynamics because Gibbs was the person together probably with Kelvin who integrated it. But as I'm going to show you a bit as we work through this, there were lots of famous people who did a major chunk. And like always, now we understand the theory very well. But when people were building the framework of thermodynamics, they actually didn't. So they didn't even totally know what pieces were missing. And that's why there's sort of not one person that can be credited with thermo. There's a few famous names that are not on here, right? Like Carnot, who probably did some major contributions, as you'll see later, to thermodynamics. But I have one more question for you. Why is it called thermodynamics? And, you know, if you're like me and you were traumatized as a young student by bad teachers, you know, I can't tell you how many times I've heard somebody say that that's the wrong title for the class. Because thermodynamics, it's all about study of equilibrium. So there's nothing about dynamics in it, right? Has any of you ever heard that? You just raise your hand. Oh, maybe teachers have wisened up. Good. So that is such a dumb thing to answer, right? Because the word comes purely from its history. I mean, where does it come from, right? Thermodynamics comes from started in the 17th and 18th century. And what were people trying to do in the 17th and 18th century? You know, they were trying to build the Industrial Revolution. And they were trying to figure out how to turn heat, burning stuff, into work, right? They were trying to build steam engines to pump water out of mines. They were trying to build steam locomotives, right? So I'll show you some history, but the early people were doing thermal. It comes from thermal, right? They were, you know, in the beginning, they just made some boiler that boiled water, and that steam would drive some kind of engine with pistons. And after a while, some guy goes like, well, I should be able to calculate how big my steam tank has to be, right? How much wood I need to put in to drive the train up the hill or something. And that's when they started doing relations between thermal stuff and dynamics. So that's where the word thermodynamics comes from. It has nothing to do with equilibrium or non-equilibrium. It's because of the coupling between thermal behavior of things and mechanical behavior of things. So I'll show you a little bit about the history in a second, but what happened essentially over 200 years is that first, people try to integrate thermal science with dynamics. So doing, you know, either mechanics or deformation. So if you think of the field, the first one that was sort of integrated was mechanics. And if you think of, like, you know, famous equations in that field and famous or important variables, well, we'll give credit to Newton, I guess, for mechanics. And the variables, the key variables and materials properties are things like velocity, force, position. And key system properties, right? So key system properties would be things like mass, right? Because Newton's equation can tell you a relation between how velocity and force relate, but to get the actual numerics, you need to know the mass of the system, right? So this was Newton. Newton lived from about he was actually born in 1643 to 1727. Another form of mechanics, this is more kinetics, right, is things like elasticity. And, you know, here you could think of the first equation as Hooke's law, right? But think of this generally as the equations of elasticity. And so important variables there are things like stress and strain. And what you need to know about materials to relate them, you need to know elastic constants or compliances, right? So in general, that's some kind of tensor, but you could say you need elastic constants or maybe the compliance matrix, right? These are two different ones. To relate these. No surprise, Hooke lived around the same time as Newton, so they were both into mechanics, right? Hooke is 1635 to 1703. Okay. So after that, so this was important stuff, right? Because this allowed you, when you start integrating this with thermal science, this allowed you the science of motion. It took a while before people made other things part of thermo. In some sense, the next big step was through the Maxwell equations. Sorry. So it was electrical and magnetic energy transfer. Of course, the key equations here are Maxwell equations. And key variables here are electric field, polarization, applied magnetic field, magnetization. And key materials variables to relate these are things like susceptibility, right? That would relate the applied magnetic field to the induction and therefore to the magnetization. And things like the dielectric constant, right? In some slightly simplistic description, the dielectric constant would relate polarization and electric field, right? Finally, we also learned a lot more about, and Maxwell, as you'll see, came a lot later, right? So Maxwell is 1831 to 1879, didn't live very long. And thermal sciences, you know, this uses stuff like Fourier's law. And here important variables are things like temperature, heat flux. And important materials properties are things like heat capacity, right? Cp, Cv. And Fourier lived around the time of Maxwell. (1768 to 1830). So why do I write this down? Because these are essentially different ways to move energy around, to either store energy or move energy around, right? You have mechanics. So a system can change its energy by changing its kinetic energy, changing its potential energy. You have elasticity, which is essentially telling you you can transfer energy into a system by applying forces to it if the material deforms under those forces. You can have electrical and magnetic energy transfer, and you can have thermal energy transfer. And most of you will have seen all these fields by themselves, right? You probably have some painful course in electromagnetism or in elasticity. But what thermodynamics will do is integrate these all. It will look somewhat abstractly at these and say, these are just different ways of transferring energy in and out of my system. And most of the time, all I need to know is like how much energy they transfer. And because of that coupling, because it treats them as the same thing largely, we will start to see coupling between these things. So what happens if you couple electrical and elasticity, right? Then you get piezo effects, right? A piezo effect is if I deform something, I can change the polarization on something, so the voltage over something. So that's a coupling between these two fields, right? I can couple thermal with electrical, right? That's pyroelectricity, right? That's, for example, how motion detectors work. Motion detectors, most of them absorb infrared, so they have a slight temperature change, and that creates an electrical pulse, change in voltage. And so in thermodynamics, these couplings will come out extremely natural. It's in some sense an integrator of all these fields. Okay, let me show something else. Okay, so you should be able to see my screen, right? I've shown here sort of the whole timeline over which this all happened. Again, in the very early part, right, you had the mechanics piece. Newcomen, who built the first steam engine, Newton, who had the apple fall on his head. And then the people that really started quantifying it, right? James Watt, where's the unit Watt comes from, right? Who was really kind of was able to start putting units on it. And then came the more sophisticated thermo piece, probably starting with Carnot. Carnot, who really figured out the second law and finalized it. And then I would say the late stage of thermodynamics, which is, you know, Maxwell, anybody who can do electromagnetism can do thermo. And then Kelvin, who was the brilliant integrator, right? Kelvin, I think, is one of the most brilliant scientists. I'm a big fan of Kelvin because he was a scientist entrepreneur. He understood thermo unbelievably well, wrote books about it. But he's also like credit, he built the first transatlantic phone cable. He invented the compass that you could use on steel ships. This was a big issue when the British Navy switched from wooden ships to steel ships they found that their compasses suddenly didn't work anymore because, aha, the ship was magnetic. So very much a scientist and engineer at the same time. And then, of course, Gibbs and Joule, right? And they were sort of like, they looked at everything backward and said, you know, I can write a book about this and totally formalize it also. Not that I recommend reading Gibbs' book, it's incomprehensible. So that's kind of enough for the history. I wanted to give you a little bit of background so you know where this stuff all comes from. Okay, so I want to give you the essence of what thermodynamics is. If you had to explain it in 2 minutes, so time me, let me tell you what thermodynamics is, right? Thermodynamics is a definition of a system and an environment where you can track the energy flows between the two, whatever they are, mechanic, kinetic, electromagnetic. The energy has to be conserved, and the reason this is so important is that the energy that goes in the system has to come out of the environment, so that if I know one, I know the other. If I measure, I get 5 kilojoules in my system, that means I got it from the environment. And then you optimize, you minimize the entropy of the system. Sorry, you maximize, darn. I didn't get enough coffee this morning. You maximize the entropy of the system plus the environment. So all that thermodynamics is this problem. The energy gets distributed so that the total entropy of the system and the environment is maximal. Everything else is derivative, okay? Everything else is crunching numbers and formalizing this. But that is all it is, okay? And so basically, how would you solve this, right? Let's think a bit here about scientists. What you would want to do is you would want to calculate, right, ds of the system as a function of dE of the system, right? And then plus ds of the environment as a function of dE of the environment, but this is minus dE of the system because you have energy conservation. Can you still see when I write there? But I think I shouldn't walk around so much, right? Can you see the bottom of the board? Okay, cool. So you see, this is basically the only equation I have to solve. So if you keep this conceptually in mind, you're going to do well. So, you know, in thermo, occasionally you're going to get into the weeds, like, oh, is this an exact differential? Is this an exact differential? Once in a while, just step back and come back to what we're really trying to do, right? So let's think about what do we now practically have to do for a system to make this into something we can actually use, right? Well, we always should very carefully define our system, right? So the first thing to do is carefully define system. Carefully define system. 2, I should know which energy flows I can have in and out, right? So I should be able to, I need to be able to quantify the energy flows. And then 3, I need to relate energy flows to entropy changes. And then, of course, if you want to tell your boss anything practical, because, you know, I don't think your boss is interested in knowing that in equilibrium the entropy is 17, right? You're going to have to relate this all to properties. And that's essentially the 4 steps of finding equilibrium. Okay, so that means the first thing you always worry about is defining your system. Do not forget to do this as an explicit step. What you're going to find is when you look at problems in the problem set, I think you will often make some implicit system definition. The problem with that is that if you don't make it explicit, you will often make mistakes. So why is the system definition important? Because the system definition controls the energy flows, right? If I take a different boundary, then my energy flows are different. And I will show you later some kind of like subtle differences of this. So a system, you have remarkable freedom in thermodynamics. It's pretty much any collection of matter that can be precisely specified. And, you know, I should add is microscopic, right? Macroscopic. But I think we know that by now. So sometimes that means it's surrounded by one boundary, and you say, you know, whatever's here is in my system. Let's say this is a drop of water, and I let it splatter on the ground. Okay, so now when I'm done, you know, my system is a bunch of tiny little drops that splattered, plus maybe a bit of a pool of water here. But that's okay. I can fully specify the system, at least in principle. I can say, you know, it's all the drops that splattered that came apart from this big drop, okay? Sometimes systems can be abstract. There's one of my favorite problems in problem set 1 is a very simple question. It asks the question, you have a tank. The tank is evacuated. So it starts being P0, and outside is P equals 1. 1 atmosphere, right? And there's some valve here. And the tank is adiabatic. So there's no heat flow into the tank or out. And the question is, I turn open the valve, so the tank fills, right? Equilibrates to 1 atmosphere. And the question is, when it's done, what's the temperature of the tank? And there's many ways you can solve this, right? You just have to know what you're doing. Maybe your logic is to take the tank as a system, right? If you take the tank as a system, then it's an open system, right? We'll talk later about what open and closed means. But the easiest solution is to imagine the gas that ends up in the tank before it's there. So this balloon of gas that forms and that gets pushed into the tank. And if you take that as your system, you'll find this question takes 3 lines to answer. You can also solve it taking the tank as the system. And it's a very different approach. And of course, it should give the same answer. But what I'm saying is, like, make sure you know which one you're taking. Okay. I'll give you another example. Sometimes we do like a piston compressing gas, right? And there's some gas in here. You get different approaches if you treat the gas as the system or the gas plus the piston. They are very different because the energy flows are very different, right? Imagine that the piston is doing friction here, right? That generates heat. If the gas is the system, so let's say now I have gas, then I only have heat coming into the system, right? Because the gas doesn't see the friction. If the whole piston is the system, then the heat flow is internal. So it's not coming across the boundaries. So then the only thing into the system is this work by which I push the piston down. You see that? So simply, when I change the system, or therefore the boundaries, how I will write down energy balances will change. Of course, the solution needs to be the same, right? A physical solution cannot depend on how I look at it, right? And this is sort of both a strength and a kind of annoying thing about thermo. It's a real strength that you cannot set up your system wrong as long as you're consistent. It's just that there's easier ways and harder ways to set it up, right? And I'll tell you, here's how you will know you get really good at thermo. If whatever way you start, you can get to the same answer. Then you've come home. And you will feel that moment, and you will feel amazing when you suddenly go like, wow, there is not just one way to solve this problem. There are like 3 ways, and they all give the same answer, but with very different equations. So. Okay, we define a system. Then we also have to define boundaries. And so boundaries tend to have a specification that usually reflects which types of energy they let through. So, you know, we will talk about, you will see words in books about permeable or impermeable or impermeable. Right? Permeable means that matter can move through, right? So permeable boundaries are an open system. And that means energy can come through just as matter, right? Matter is a form of energy flow as well, right? You know, if I put gasoline in my tank, and hopefully not for long anymore if we have electric cars, but if I put gasoline in my tank, that is a form of putting energy in my system, right? If it's impermeable, that's saying, well, the system is closed. We will use words like adiabatic boundaries or insulated that is a statement of no heat flow, right? We will make statements about, we'll call boundaries diathermic. That means perfect heat flow. So the system is always at the same temperature as its environment. Or you could say infinite heat flow, right? So for every type of heat flow, for every type of energy flow, you can think of a boundary that allows it or does not allow it. So boundary, which type of boundaries you have is 100% coupled to which type of workflows you have or heat flows. So for example, if I say something is rigid, so non-deformable, what am I really saying? When something is rigid, I'm really saying I cannot do mechanical work on it, because mechanical work is force times displacement. And if you don't have a displacement, you don't have work. So rigid really means like no mechanical work. One of my colleagues describes a good graduate student also as work times displacement. You can be smart and not get anything done. That's also zero energy transfer. Or I guess, or not smart and getting a lot of things done, but we don't have that problem among our graduate students. So remember, energy transfer is a product of two things, right? It's not just the result of a force. Okay, so you can have deformable boundaries. In this case, you will have mechanical work. And I can keep on going, right? I can invent boundaries that let just one type of matter through, like maybe, you know, I could make a membrane that just lets one type of ion through, right? So a selective membrane, maybe it lets oxygen through or hydrogen. And we will kind of play with boundaries like that. They will become very important in electrochemistry. Then, since we're at definitions, I want to add something. When we talk about variables to describe a system, there's an important distinctions in thermodynamics between extensive and intensive. So extensive are the ones that scale with the system size, and the intensive ones do not scale with system size. So examples of extensive variables, you know, volume, mass numbers like Ni. So if I have 1 mole of gold in my system, if I double my system, I have 2 moles of gold. So that's an extensive variable. Things that do not scale are things like the temperature of a system. It's an average quantity, as we'll see later, the pressure, you know, etc. Electric field is an intensive variable. Sorry, no. And then there are normalized extensive variables. So, for example, if I take the mole numbers or something and I divide by the volume, right? Then I have something like a concentration, right? Or maybe this could be, sometimes N is expressed as number of atoms, sometimes it's number of moles. But if I divide by the volume, I get a concentration. if I divide the volume by the total number of moles of something, I get the molar volume, right? Which I'll write with a small v. So molar volume. So by definition, these variables are not extensive, right? Because, oops, I divided the extensivity away by dividing by an extensive variable. But they are not intensive variables either. They are called fields. Or densities. Actually, let me not call them fields. I think it's going to lead to confusion. So they are definitely called densities. And what you have to keep in mind that they will play the same role as extensive variables. So in thermodynamics, we will make a very significant distinction between extensive and intensive variables. So when you see normalized ones, you may think, well, those are not extensive, but they will play the same role as extensive. They're just sort of by accident, I guess, not really by accident, but they're normalized away. Okay. Okay. I don't think that board wants to flip, so I'll just go here. So one confusing topic in thermodynamics is what are variables needed to describe a system, and they're often called state variables. To fully formally define what are state variables, I need to teach you a little more. So what we're going to do is we're going to take on a working definition and then refine it. And I hate to say, at this point, the definition is whatever we need to describe the system. And then we'll start refining that by next lecture already. So, you know, there's your obvious candidates, right? Temperature, pressure, volume, you know, mass numbers, maybe the number of moles of I, the number of moles of J, whatever, right? But don't forget that there could be other important variables, right? Like maybe the color matters at the boundary, maybe the shape matters. Why do you think they would matter, given what I told you? Why would color ever matter for a system? Think about it. It's time for somebody to speak up since we're almost done. It was on the other board, but I erased it. How could color matter as a variable? Well, imagine that you had energy transfer by radiation, right? Then the color would matter because it would control how much of radiation is absorbed by the system. So color would be an important either parameter or variable, depending whether it's changing or not, because it would determine how much energy is coming in from that external field. Well, imagine that you live in a stress field, right? A non-homogeneous stress field, something that's a little more complicated than just isotropic pressure. Well, if you live in a complicated stress field, then the shape of your object interacts with that stress field, right? Whether I have a needle or whether I have a sphere with the same volume, they will have different interactions with the stress field. So they will have a different way of absorbing energy through the stress field, right? So you may have not seen these variables before, but in their generality, they matter, okay? If you're trying to do general thermodynamics. Okay. I think I'll stop here for, since we only have a couple minutes left. And I know having lecture on Zoom is a bit painful. So anyway, I hope you enjoyed it. I hope to see you on Friday. So we will have a lecture on Friday so we can kind of make some headway here. If anything went wrong here, like that you think we should do better, it's hard for us to be on the other side, and although I will ask the GSIs what we need to fix. If you can't read the board, if I walk around too much, so because I know that the camera focuses on me and not on the board, you know, we really appreciate your feedback since we're all kind of learning how to make this as good as possible for you. So, well, thanks for being here for the first time, and I'll see you hopefully Friday, bright and early, 8:10. So. Bye.